Okay, let's go ahead and get started today. Today we're going to look at some movement in a little bit different way than we did before. And let's go ahead and just dig in here. So digging in, so far all of the games and programs that we've written that had stuff move around on the screen moved only in the cardinal directions, meaning left, right, up, and down. And we use the WASD keys, traditional keys for kind of controlling something in a game. So A moving left, D moving right, W up, S down. And that was done, the way we made something move was we modified a variable by some amount. So in other words, if I pressed, for example, D, then I would say the player's X variable, add 5 to it. And that makes it so that that moves across the screen a little bit to the right. If I subtracted 5, it would move a little bit to the left. If I took the Y and subtracted from it, I'd move up. If I added, I'd move down. But notice that that's not realistic. In the real world, things don't just move side to side and up and down. So for example, if I take this pen and I like throw it, notice it, it's kind of blurry on there, but it kind of follows a path. Or if I throw it at an angle, I can move this at any angle that I want. So think about like billiard balls on a pool table. They aren't just constrained to move left, right, up, and down. They can move at angles, and they can also change their speed. So here we have this constant speed of 5. We might have friction where the thing starts to slow down as it moves around. So in other words, we want to move towards something more realistic that's going to allow us to do some physics kinds of things, and some things other than just left, right, up, and down at a constant speed. Now, for a more realistic system, we want a method to move game objects in any direction at any speed. So we need to store the direction, we need to store the speed in variables of some sort. And then we're going to use that direction and speed to then update the position or the coordinates of that object. So the object is somewhere on the screen moving at an X and a Y, or its X and Y need to change as it moves at some angle at some speed. So let's look at a picture of more what we're talking about here. So here are maybe some variables we'd have for creating this thing. So consider a ball. So here's a ball, and it's moving in some direction at some speed. So here's where it is right now, 400, 300, and it's moving in some direction. It might not be directly left or right or up or down. It could be at an angle. It could be directly sideways, side to side, or up and down, but it could also be anything like 1 degree or 45 degrees, or it could be moving down this way at negative 60 degrees or whatever this is down here. It could be moving any way on the screen. And the fact that it can move any direction and any speed. The cat is attacking my leg, sorry. All right, the cat just hit me and ran away. All right, so anyway, the main thing to be concerned here is how are we going to take this direction and speed and figure out where the new position that ball needs to be? Where is the new X and the new Y for it? Now, here's a little bit better drawing of that. So here's the X and Y where it is now. It's moving at some speed, at some angle. We're defining 0 as directly to the right here. So where does it end up? So to move the ball, we need to update the X and Y position, the ball X and ball Y, to a new position that it moved to based on the direction and the speed. So to compute that, we're going to need to compute the displacements along each axis. In other words, if I want to know where the ball ends up in X, I need to figure out how far did it move in X and how far did it move in Y. But I don't have dx and dy right now. I don't have those displacements. I need to calculate those. All I have is the speed and the angle. So how can I compute the dx based on this angle and that speed? Now think of the speed as like the hypotenuse of this triangle. So what we have is the hypotenuse and the angle. We need to figure out how much of that motion at that speed and this angle, how much of that is x and how much of it is in y. So how do we calculate that? Now, the answer to that is we're going to use a little bit of trigonometry. And maybe you have already done enough trigonometry you could figure out, all right, given that and that, how do I solve for dx? Given this and this, how do I solve for dy? But I'm going to do a quick review here. So first review item here is radians. So radians are a mathematically natural way to measure angles. Degrees are totally fabricated and made up by humans. In other words, using degrees to measure angles is kind of arbitrary. Somebody just made that up and said, well, let's divide up the circle into, I don't know, 360 units. And so they just made that up. Now, 360 is not, it's not completely random. There's a reason for that. The 360 is, you can divide it in half and into quarters and into fifths and into tenths and into 36ths and into 18ths and into sixths. There's a whole bunch of things that it divides evenly by. So it's kind of a special number that way. But it's not the mathematically natural way to measure angles. Radians is the mathematically natural way to measure angles. And here's why. If we assume that we have a circle, and we have a circle that has a radius of 1, so let's say this is the radius, and we're going to rotate that radius of 1 around, or walk around the outside of that circle with a radius of 1, then we're going to cover a distance as we walk around the outside of the circle. And depending on how far we've walked, that's going to put us at a certain angle around the circle. So in other words, if I have a radius of 1, how far is it all the way around the circle? Well, think about back to like what pi means. Pi is the ratio of the circumference to the diameter. Well, in this case, we have a radius of 1, so the diameter is going to be 2. So that means the distance around that circle is going to be 2 pi. So, circle with a radius of 1, how far is it to walk all the way around? The answer, 2 pi. So in other words, that is the same as, can be thought of as the same as 360 degrees. So to walk all the way around the circle 360 degrees, we would cover a distance, if we measured this arc length around the outside, we would cover a distance of exactly 2 pi to get back to where we started. So if we had a 1 mile radius circle, we would walk 2 times pi miles to get back to there. So 6.28 whatever miles it would take to walk all the way around there. Now notice if I walk part of the way around, like what if I walk halfway around the circle? So how far is it to walk halfway around the circle? Well, starting here and walking halfway around the circle to there, well, if 2 pi was all the way around, then it's half of that. So it's going to be 2 pi over 2. 2's cancel out, or pi. So 180 degrees is the same as pi. And notice this is mathematically natural. This 2 pi to go all the way around, pi to go all the way around, because pi is a number that is what it is. It'd be the same for an alien species somewhere across the galaxy who came up with their own numbering system. Pi would work the same way. It would always have that same ratio no matter what. So they might come up with the same way of measuring angles, but it's unlikely they would come up with this 360 or 180 degrees, because that's not the mathematically natural way. Now, to further that, let's look at what a quarter of the way around. So a quarter of the way around is half the way around. So that's going to be pi over 2, or 90 degrees. So 90 degrees is pi over 2, 180 degrees is pi, 360 is 2 pi. And really, because of how this works, any distance we walk corresponds to some angle. So that gives us this chart that looks like this, where 0 and 360 are 2 pi, 30 degrees is pi over 6, 60 degrees is pi over 3, 90 is pi over 2, and so forth all the way around. And in fact, we can compute or convert from degrees to radians really easy. Every 1 degree, if you think about that, well, there's 180 degrees to get us to there, and that was pi. So 1 degree is 180th of 180. So pi over 180 or 0.017453 radians is equal to 1 degree. And we can also say, well, what's 1 radian? Well, we just invert this. So pi over 180 degrees. So 57.2958 degrees is 1 radian. Now that seems like a weird number, but again, notice how nicely the math works out here with this being fractions of pi all the way around. And again, radians are the mathematically natural way to represent angles, so that's what the math libraries in Python use. That's going to be important to us. Now, back to our problem. Given the speed, the ball speed, and the ball angle, how do I compute the dx and dy? So in order to do that, it's important to note that that makes a triangle. So the dx is this leg, or the adjacent, to the hypotenuse, and the dy is the opposite to the hypotenuse. If you remember your trig sine and cosine functions, there's that whole SOHCAHTOA thing. If you remember that, that's great. I'm going to teach this a little bit differently, kind of more back to the concept of what we're dealing with on the screen here, where we have this ball and it's moving along x and it's moving along y, and we have the angle, we have the speed. So I'm going to review sine and cosine for a second. So the idea there is if we walk around that circle again, just like we were measuring those angles, we would notice if that's a unit circle, again, a radius of 1, then we might notice that the distance to the x and y axes changes. So in other words, how far to the left and right, or how far up and down am I? So if I start at 0, right there, I haven't walked anywhere, then my dx is 1. In other words, this hypotenuse, or this leg of the triangle down here is 1, but the dy is 0. The triangle is infinitely small. So in other words, what that's saying is if I'm right there on the triangle where the mouse pointer is pointing, I don't know if you can see that or not, but right there. Oh, my battery is running low. I'll have to pause this and then plug in a second. Actually, let me do that real quick and I'll be right back. Okay, so we're back. I went ahead and plugged in, so we should be good. All right, so anyway, we're right there. We are nowhere above and below. We're at 0 above and below, and we're at 1.0 to the right, so positive 1. Now, if I walk around here to 90 degrees, or to pi over 2, notice we have a dx of 0. We're right on the x-axis. We're right on 0 for the x-axis. And on the y-axis, we're at 1. And if I keep walking down, then the up and down goes down back to 0. But now the x is at negative 1. And if I keep walking around, x now starts to shrink and goes back down to 0. And y goes to negative 1. And then if I walk back around a little more, that x will then start growing back to 1, and y will go back to 0. So that will continue. So sine, the sine function gives us the distance above or below the line, or up and down. And cosine gives us the distance to the left and right of that. And one of the ways, just like you can remember that SOHCAHTOA thing, to remember how to do this, one of the things that I like to remember when we're dealing with in kind of games on the screen like this is sine is up and down. So if you think about you sign up for something, there's some event, you sign up for it, then that is sine is up and down. Cosine is left and right. All right, now, if we go ahead and chart the sine and cosine as we walk around the circle, we get that typical wave that you're used to seeing with it. So in other words, this is 0. So notice that when we start out right there, where are we on sine? Sine is up and down. So where are we above and below the line? We're right on 0. And as we walk, that will, around the circle, that will grow till we're at 1. And if I keep walking, I'll walk back toward the circle again. So in other words, I walk away from it all the way till I get to 1. And as I keep walking, I head back down again till I'm back at 0. And if I keep walking, I now go negative below the line till I'm at negative 1. And if I keep walking, I go back up. So you can kind of see that pattern here. Walking to 1, walking back to 0, walking to negative 1, walking back to 0. But as I'm doing that, if I also chart how I'm moving left and right, not just up and down, that's cosine. So right here, I start at 1. And as soon as I start walking, I start heading toward the vertical 0 point, the x-axis being 0. I eventually hit 0, and then I go negative, and then I eventually get all the way over here to negative 1, and then I head back towards 0, and then back to 1 again. So you can see that kind of repeating itself both in the positive direction and in the negative direction. And that's going to be something that's fairly useful for us to look at or think about, that we can represent something as a negative angle to get down here, or a positive angle going all the way around there, and it's the same. Notice that this thing here is there, that's at 0. If I walk all the way around, I get back to where I started again. Same thing for sine. There I'm at 0, walk all the way around, back to where I started again. Okay, so back to our problem. So given the speed and the angle, how do we compute dx and dy? All right, so dx, that's left and right, so that's going to be cosine, so cosine of the angle. And in this case, I'm going to multiply it by speed, because notice in our diagram back here, this radius was 1.0. That was a radius of 1. Radius of 1. But over here, the radius is ball speed. So what we do is we take that radius of 1, and then we're going to scale it either up and down by speed. So speed is 1.0. It's just the same as cosine, but if speed is 2.0, that would be twice the cosine, 2 times the cosine. And really, the reason that this works to just multiply the sine of the cosine by speed is just similar triangles. In other words, if you have a triangle that has twice the speed, then the dx is twice as big and the dy is twice as big. If I have a speed that's half of 1, like 0.5, like right there, then this is half, and that would be half. And so it's just similar triangles that we use to do that, to scale that triangle either up and down to match the size of this hypotenuse, which is our speed. So there's our calculation for that. In Python, to perform those trig operations, we're going to use the math module. And to use that, we just import math. And then the functions that are available there, math.sine, math.cosine. One thing to note about the sine and cosine functions, the angle that we provide has to be provided in radians. Again, the mathematically natural way to provide that. Now, to help us with conversion to radians and degrees, there are actually some functions in the math module to that as well. Math.radians, if we pass it a number of degrees, it will convert it to radians for us. If I pass into math.degrees a number of radians, it'll convert it to degrees for us. Okay, so let's take a quick look at how to use those. And we're going to write some code here. So I'm going to switch over to Python here in just a second. Let me finish getting through this first. All right, so the idea is before the loop, we're going to import stuff like the math module, Pygame, things like that. We're going to initialize all of that stuff, make the display surface. Then we're going to initialize those object variables. And those object variables are going to include an angle and a speed. And then inside of our loop, what we're going to do is we're going to do the typical things, but we're going to compute those displacements, dx and dy, and we're going to update the object's position. And then we're going to render everything on the screen. So the only things that are different here are this computing of these displacements. All right, so let's go ahead and write some code. I'm going to switch over to the to Python here. And let me get this so you can see it on the screen. All right, so that doesn't look too bad. Actually, let me move it over right about there. All right, so this is going to be all right, so to start out with, I'm going to use Pygame, just like we have for a lot of other things. I'm also going to import math, because I know I'm going to use that. And then because I'm going to use Pygame, I need to do a pygame.init. I'm going to need a display surface equal pygame.display.setMode. And I'm going to make this 800 by 600 like we've been doing for a lot of the other examples. Okay, now we have our display surface. And now before I write any of the code for the bouncing ball, I'm going to go ahead and just flesh out the rest of the skeleton of this. So while true, inside the loop, we're going to need to process some keyboard events to do things eventually, at least escape to exit. So I'm going to do pygame.event.pump. And then I'm going to need to get the keys. So keys equal pygame.key.getPressed. And now if keys pygame.k underscore escape. So if they press the escape key, then we're going to break out of the loop. Now I know at the bottom of the loop, I'm going to have to update the display to see stuff. So pygame.display.update. we're going to need to call that. And then after the loop, I'm going to close the window. So pygame.display.quit. And I'm probably also going to want, at the top of this rendering thing here, I'm going to want to clear the screen. So display surface.fill, and I'll just fill it in with black. Okay, so there's our skeleton of our code. We haven't added any of this stuff to have the ball moving yet, but let's just make sure that we have this working. So we'll run that. I'll save it as ball.py. And let me move this down so you can see it. So there's the window. I hit escape. It goes away. So all that works. No errors show up here. Let's go back and add our code for the ball. So now for the ball, let's start it out at right in the center of the screen. So 400. Now let's give it a speed. So ball speed. Let's set this equal to, let's set it just to equal 1.0 right now. We can change that later. And let's set the angle. And let's set the angle to 45. And notice that I'm using this in degrees. So we're going to have to convert that when we go to use it in the code. So I'm going to put a little comment up here. Those are the variables that we're using for the ball. And you really, maybe that's not necessary because we called it ball x, ball y, ball speed, ball angle. Now inside of the code down here though, now in here is where I want to update the position of that ball. But to do that, we have to calculate or compute the ball displacements. So that's the dx and dy. So dx is, that's the left and right. So that's changes in the x. So to compute that, that's going to be ball speed times, so that's the scaling factor, times math.cosine, because cosine is left and right, of, and this is going to be ball angle. Now, there's a problem that we have right now with that code, and you may have already noticed it. The problem that we have right now is that ball angle is in degrees with 45, and cosine expects it to be in radians. So to convert that, math.radians of ball angle. So that says convert the degrees into radians, pass that to cosine. Cosine will then come up with that value between 0 and 1, or negative 1 and 1, and then we are going to scale that value up or down by the actual speed. Now we're going to do the same thing for dy. The only difference here is that we're going to use sine instead of cosine. Everything else is the same. So sine is giving us the opposite, cosine was giving us the adjacent. And then we're still multiplying it by the speed in both those cases. Now there is one change we're going to have to make, but I'm going to let the problem happen first. So that's the displacement. Now to apply the displacements, we just now need to add them to the ball x. So in other words, to get to the new positions, it's going to be ball x plus equal dx, and ball y plus equal dy. And so now we're at a new position. And one final thing, well let's run this and see what happens here. Now we need to draw the ball. So in here, let's just do a pygame, pygame.draw.circle on the display surface with a color of, let's make it a red ball, that, and a position of ball x, ball y, and let's make it a radius of 10. And let's make it filled in. All right, let's run that and see what happens. Now, notice something interesting happened here. It says that there's a type error, integer expected got float. And the reason for that is, and I really wish they had done this inside the function, but the circle function expects this to be a whole number of pixels for x and a whole number for y. You're not allowed to have fractions like a half a pixel. And so to fix that, we just need to convert these to integers when we pass them in. I don't know why they didn't do that inside the function in Pygame. So we have to convert it there. All right, let's run this again. There's still one problem. We'll see that here in a second. All right, so there it went. It left the screen. So let's make it so it wraps around. So here, wrap ball around. So to wrap the ball around on the screen, I'm going to do a set of if statements. So if the ball x is ever greater than 799, then to wrap it around to the other side, ball x equals 0. And if ball x is ever less than 0, then ball x equals 799. So that's wrapping it around the left and the right. Now let's do the top and the bottoms. If ball y ever gets to be greater than 599, then ball y equals 0. So in other words, if it goes bigger than 599, we set it back to 0 on the other side. And here, if ball y is ever less than 0, then set it equal to 599. So that's going to wrap it around the screen edges. Let me take out some of these extra spaces I added in here. Now, there's still one thing that's a little strange that we're going to find in a second. Let's run that. So there it is. Let me move that so you can see it. But notice that it's moving at an angle of 45 degrees. Now, the strange thing is 45 degrees is typically not considered down. It's considered up. It'll be considered this is 40. This is 0. 45 is here. 90 is that way. So let's just see what happens if I put in 90. So let's start this off at 90. We'd expect that to be straight up. But something weird happens. It's straight down instead of straight up. Now, why is that? The reason for that is because it's pretty simple. And the reason for that is that the screen, remember, is different from normal Cartesian coordinates. In normal Cartesian coordinates, 90 degrees is straight up and 0 degrees is straight down. But our coordinate system, the y is inverted. In other words, it gets bigger going down rather than going up. So to fix this, what we're going to do is actually going to be something pretty simple, that when we compute this dy, we just have to invert it. So because the y-axis is kind of upside down from normal Cartesian system, we just have to do a -1 times that, and that will invert this whole thing. So now 90 degrees will be, as expected, straight up. Now let's add one more little bit of code to this to make this a little more interesting. Let's make it so that, notice we can change the speed, change the speed, change direction. So right now we have a speed of 1. If I want that to move slower, or faster, I could say, like, let's make it move 0.5. And now it will be half the speed it was before. And if I want it to move really slow, I can make it 0.1. And if I want to change the angle, instead of 90, let's make this like 10 degrees. You'll notice it'll move kind of along this line in a very shallow upward direction. And now let's just make it so we can kind of control that a little bit. And I'm going to make a really simple control on this right now. I'm going to say if keys pygame.k_, let's use the space bar. If you press space, I'm going to give the ball a random angle. To do that, I need to import random. And down here, when they press space, I'm basically going to do the same thing that I did up here. But I'm going to make this random. And let's go 0 to 359. So any of the 360 possible angles, let's run that. And now you can see the, oops, typo. So there it is. I press space bar. I get different directions. Let's make it a little faster. That's a little bit too slow. And notice if I hold the space bar, I keep getting new angles, and then I release it and it goes off in some direction. Okay, let me put that whole thing on the screen so you can see it. And if I wanted, I could actually make it so I could drive that thing too. So I could add keys to change the angle or change the speed. Let's quickly do that. I'm going to add an A and a D key to just change the angle. I'll leave the speed alone. I'll leave it as an exercise to you to figure out how to change the speed. So if keys, let's say pygame.k underscore, so I was going to use A. So A I'm going to use to increase the angle. So ball angle plus equal 1. I'll do the same thing. So if they press D, ball angle minus equal 1. So this is just changing the angle of travel. Let's run that. So there it is moving. And if I press A, it kind of steers in a kind of counterclockwise way. If I press D, it goes in a clockwise direction. So now I can drive this thing kind of like a little go-kart around on the screen. And if we wanted to, we could add keys to speed up and slow down, to add like a gas pedal and a brake. But notice that now we have the ability to have objects that move at any direction. We're also going to later on add the ability to have things like this where things wiggle back and forth. You fire like a homing missile, it squiggles back and forth, and we can have a lot of things moving on the screen at one time. But the key to doing this is really pretty simple. It's just sine, cosine, and understanding how to use those to solve for the displacements in x and displacements in y, and then apply them to the position we're in, update the position, and then we get something that's more complex like that. Okay, so let's go back to the presentation for a second. If I can, having technical difficulty here. All right, hold on 1 second. I think I accidentally closed it. Okay, and we're back. And so essentially what we did is we went through all of the code that we just went through. And that's all we're going to cover today. So everybody stay safe. I am going to post the sample code, and we are going to have a new lab coming up shortly as well. So look for that. That won't be today. That'll be coming up in either the next class or the class after that. And what I want you to do today, though, is to get that code working like I had there, but maybe add W for speed up, S to slow down. Keep in mind you might need to cap that and have a maximum speed, that if it goes above a certain speed, you don't let it go faster than that. Also, maybe you have a negative, a low cap, where if it gets to 0, you don't let it go negative. You don't want to drive backwards maybe, so you stop it there. So I would play around with that code and try to add those things and see what you can come up with. But this trigonometry we just did, as simple as it was, sine, cosine, understanding how radians work. Sine is up and down. Cosine is left and right. Scale that up using the speed. We're going to do a lot of stuff with that trigonometry that's going to allow us to do some really cool stuff, including applying things like friction, gravitation, forces between things. You can make an explosion that blows things away from the center of it. You can make something where one thing colliding with another has an impulse, or the ball bounces off the walls rather than just running into the, or wrapping around. And so a lot of that stuff is going to be possible, so we'll look for that. But that's all we're going to do today. So I'll go and stop there. Everybody stay safe. Send me something or a message if you have questions. Send me a text message. Shoot me an email. I'm around, and I'm happy to come in and sit down with you and explain things if we need to. All right, so that's it for today.